Here's a fascinating equation. X to the power of x equals 10. At first glance, this looks impossible to solve with our usual algebraic tricks, but hidden within this equation is a doorway to one of mathematics' most elegant special functions. Before we begin, a rigorous analysis requires us to define the domain of x. What values of x are we permitted to investigate? If x were negative, x to the power of x becomes problematic. For instance, at x equals negative 1/2, we'd get a complex number. The function is only well-defined for select rational values and is not continuous. Since we're seeking a real number that equals the positive value of 10, we can confidently restrict our search to the well-behaved continuous domain where x is greater than 0. This isn't an assumption, but a logical deduction. Let's now proceed with our algebraic toolkit on this restricted domain. We begin with our original equation. The primary difficulty remains. Our variable x is in both the base and the exponent. To handle a variable in the exponent, the standard technique is to apply a logarithm. We'll take the natural logarithm of both sides. We now invoke a fundamental property of logarithms. The log of a number raised to a power equals that power multiplied by the log of the number. Applying this rule to the left side will bring the x down from the exponent. This simplifies our equation to x times the natural log of x equals the natural log of 10. And at this point, we've reached an impasse. There's no way to isolate x using a finite combination of elementary functions. To proceed, we must introduce a special function. Before we solve our problem, let's take a moment to truly understand the tool we need. Welcome to a masterclass on one of mathematics' most elegant special functions. The Lambert W function is named after Johann Heinrich Lambert, an 18th century Swiss mathematician who encountered similar equations in his work on transcendental functions. However, the function wasn't formally defined until the computer age made such calculations practical. The story begins with the deceptively simple equation. Z's times e to the power of z equals y. This form appears constantly in mathematics, yet there's no algebraic way to solve for z. Let's build intuitions with some examples. W of e equals 1, because 1 times e to the first power gives e. W of 2e equals 2, because 2 times e squared gives 2e. And w of 0 equals 0. The defining property is beautifully symmetric. W of y times e to the power of w of y always equals y. This is what makes it the perfect inverse for our exponential logarithmic equations. To truly understand the Lambert W function, we need to visualize the relationship. Let's start with the function we want to invert. F of x equals x times e to the power of x. Here's our function in blue, with the identity line y equals x in gray. Notice how the function decreases from negative infinity, reaches a minimum, then increases without bound. The critical point occurs at negative 1 over e, approximately negative 0.368. This is where the derivative equals 0, marking the boundary between decreasing and increasing behavior. This minimum value is crucial. The Lambert W function can only accept inputs greater than or equal to negative 1 over e. Below this threshold, no real solutions exist. The upper branch in green is the principal branch, w subscript 0, which gives the larger of the two possible solutions. The lower orange branch is w subscript negative 1, giving the smaller solution. Here's the key insight. For positive inputs like the natural log of 10, only the principal branch w subscript 0 gives a real positive result. This is exactly what we need for our problem. The two branches exist because the function x times e to the power of x is not one-to-one on its entire domain. Between negative infinity and negative 1 over e, each y value corresponds to two different x values, necessitating two branches for the inverse. Now, armed with this deeper understanding, let's return to the equation that started it all. Our goal is to reshape the left side into the form z times e to the power of z. To do this, we'll rewrite x as e to the power of its own logarithm. This subtle move unlocks the substitution we need. Now that our equation has the correct structure, let's make the substitution explicit. We'll let z be equal to the natural log of x. With this substitution, our equation perfectly matches the Lambert W form. By definition, we can now apply the principal branch of the Lambert W function to solve for z. This gives us that z equals the Lambert W function of the natural log of 10. Now, we simply substitute back the natural log of x for z. We are now on the final steps of isolating x. To undo the natural logarithm, we perform its inverse operation, exponentiation. We raise e to the power of both sides. Because the exponential function and the natural logarithm are inverses, they perfectly cancel each other out. And there it is, a closed-form solution that elegantly connects exponentials, logarithms, and the Lambert W function. Beautiful, isn't it? We've found a solution, but to be fully rigorous, we must prove it's the only real solution. To analyze the function f of x equals x to the power of x, we must find its derivative. This is a non-trivial step that requires a technique called logarithmic differentiation. First, we take the natural logarithm of both sides. This gives us the natural log of y equals x times the natural log of x. Now, we differentiate both sides implicitly with respect to x, using the product rule on the right. This yields 1 over y times dy by dx equals the natural log of x plus 1. To find the derivative, we solve for dy by dx by multiplying by y. Finally, we substitute y equals x to the power of x back into the equation. And there's our derivative. For positive x, x to the power of x is always positive, so the sign of the derivative is determined by the term natural log of x plus 1. This means our function rises steadily for all x greater than 1 over e. Therefore, it can cross the horizontal line y equals 10 exactly once, confirming our solution's uniqueness. Let's now calculate the numerical value of our exact solution. First, we evaluate the innermost part. The natural log of 10 is approximately 2.3026. The principal Lambert W function of this value is approximately 0.9188. Finally, calculating e to this power gives our solution, approximately 2.5062. Plugging this number back into the original equation confirms our result. Let's visualize this one last time to bring it all together. Here's our function in blue and the line y equals 10 in red. The intersection point marks our solution, the very same value we derived analytically. A perfect match. But what if we didn't have the Lambert W function? We could still find the answer using a numerical technique like Newton's method. Newton's method is a powerful iterative process for finding the roots of a function, that is, where the function equals 0. It starts with an initial guess and repeatedly refines it. For our problem, f of x is x to the power of x minus 10, and we've already found f prime of x. Let's substitute these expressions into the general formula. This gives us the specific iteration formula for our problem. The beauty of Newton's method is that it uses the tangent line at each point to predict where the function crosses 0. Let's start with an educated initial guess. Since 2 to the power of 2 equals 4 and 3 to the power of 3 equals 27, our solution should be between 2 and 3. Let's try 2.5. First, we evaluate our function at the initial guess. 2.5 to the power of 2.5 is approximately 9.88, so f of 2.5 equals negative 0.12. Next, we evaluate the derivative. Using our formula, f prime of 2.5 is approximately 18.9. Now we apply the Newton's method formula. Since f of 2.5 is negative, we add the correction term, giving us x1 equals 2.50635. Let's verify our progress. 2.50635 to its own power gives approximately 10.003. We're incredibly close already. After just one iteration, our guess is already accurate to 3 decimal places. The second iteration gives us 2.506182, which matches the Lambert W solution to 6 decimal places. Newton's method converges so rapidly here because the function x to the power of x minus 10 is smooth and well-behaved near the root, with no sharp turns or discontinuities that could confuse the algorithm. From an impossible-looking equation to a precise solution, all connected through one elegant function, this is mathematics at its finest. You'll encounter this remarkable function again in population dynamics, quantum physics, and even combinatorics. It's one of mathematics' quiet universals. Thanks for watching. If you enjoyed exploring the Lambert W function and seeing how different mathematical approaches converge to the same beautiful result, please give this video a like and subscribe for more deep dives into the elegant connections that make mathematics so fascinating.